Have you ever wondered what nature looks like on the smallest scales? What exists inside the atom? And what laws govern the smallest of particles? This frontier in science was largely unexplored until the turn of the 20th century. During the 1900s, scientists would learn more about the quantum frontier, creating one of the most effective and accurate theories to date, quantum mechanics. The scientific theory of quantum mechanics, describing the universe at the tiniest of scales, is one of the most important theories to ever be created. It was developed by genius physicists who explored the quantum realm and found completely new ideas about reality. Today, these discoveries have provided us with amazing new technologies and a step forward in creating a complete theory of everything. Quantum mechanics began with two main discoveries. The first, in 1801, was the discovery that light wasn't a particle, as previous studies had shown, but a wave. This was proven by the double slit experiment, where light was shown through two slits, creating an interference pattern characteristic of waves. Thomas Young, after originally doing the double slit experiment, stated in an 1803 lecture that, and I quote, "We are fully authorized to conclude that there must be some strong resemblance between the nature of sound and that of light." The next major discovery happened at about 1900, when a problem called the ultraviolet catastrophe was being investigated. The ultraviolet catastrophe involved problems with the current theory of blackbody radiation. The solution, theorized by Max Planck, was that light exists in packets or units called quanta. Albert Einstein would then prove the existence of light quanta, called photons, using the photoelectric effect. These two discoveries, and the apparent contradiction between them, would create the basis of quantum mechanics. The theory reconciling these two discoveries would be created in a 1924 thesis paper by the physicist Louis de Broglie. He discovered the mathematical relationship between the momentum and wavelength of a particle, revealing the wave-particle duality central to quantum mechanics. In addition, the structure of a particle wave would be revealed when the physicist Erwin Schrödinger created his wave function equation. This groundbreaking equation was used to describe and calculate the structure of particle waves. It became understood that all particles had wave-like properties, and these waves describe the probability of finding the particle at a location. These waves were smeared out, and meant that it is impossible to know the precise location of a particle until it is measured. When measured or interacted with, this wave function will collapse and the particle will appear at a single area. But before measurement, the particle exists as a wave of probabilities. This explains the double slit experiment and an interesting variation of it. In this variation, the slit each photon entered was measured. The resulting pattern matched that of a particle. By measuring which slit the light goes through, the resulting pattern was somehow affected. This is explained by the wave function and existence of probability waves. When we didn't measure the light when it hit the slits, it remained a wave and created an interference pattern. When the probability wave hit the board, it was measured and became a particle. The particle was more likely to form in certain regions, so those areas were hit more often, creating an interference pattern. But when the light is measured at the slits, it collapses into a particle and creates a particle pattern. This probability wave nature of matter results in many seemingly impossible effects. One is quantum tunneling. Since particles can also be represented by wave functions that are smeared across space, it's possible for particles to appear on the other side of a thin barrier, as its wave function creates a small chance of a particle being in a location on the other side of the barrier. Our understanding of atoms was also completely changed by the wave function. Since electrons around an atom are probability waves, they can't be found in a single area, but exist in a cloud where some regions are more likely to have an electron. These revelations created the Schrödinger model of the atom, discovered by, of course, Erwin Schrödinger. The model superseded the previous Bohr model of electrons orbiting the nucleus, and describes how atoms are surrounded by probability clouds where some regions are more likely to have an electron. The Schrödinger model is an example of the probabilistic universe created by quantum mechanics. The position of an object isn't the only thing that collapses upon measurement. Particles can also be in a superposition of other states. Superposition is when a quantum object, such as an electron, is either in one state or another until measured. Upon measurement or interacting with the particle will immediately collapse into one of two states. However, before measurement, the particle isn't in either state. It's in both states at once, only choosing a state when measured. Two particles can also have their superpositions linked, making them entangled. Quantum entanglement is when measuring one particle, which collapses with superposition, also collapses another particle superposition. Quantum mechanics also provides a complete theory of particles, known as the Standard Model. Particles are categorized by traits such as spin. Spin is a quantum number, or a value that all particles have. It was discovered by Wolfgang Pauli after another physicist, Paul A. M. Dirac, created an equation to combine quantum mechanics and special relativity. Spin is described as intrinsic angular momentum, and particles can either have an integer spin or 1/2 spins. Any particle with 1/2 spin, or a multiple of 1/2, is called a fermion, while a particle with integer spin is called a boson. These classes of particles behave very differently. Fermions follow the Pauli exclusion principle, which states that no two particles in a system can be in the same state. Wolfgang Pauli, discoverer of the Pauli exclusion principle, would propose that an electron state depends on 4 quantum numbers, and no electrons can have the same value for all 4. Thus, the exclusion principle prevents electrons from all being in the same electron shell in an atom. On the other hand, bosons have much more strange properties, such as being virtual, carrying out forces, and creating superconductors and superfluids, fluids with no viscosity. All the particles in the universe belong to either class, fermions or bosons. The Standard Model of particle physics is a massive equation that describes the 12 fundamental fermions and 5 fundamental bosons. One of these particles, the neutrino, was actually predicted by Pauli decades earlier. To make the Standard Model even more complicated, Dirac would theorize that each particle has an antiparticle counterpart in the opposite charge. He would be proven correct, and that's how antimatter was discovered. Now, all this technical stuff is really interesting, but what most people really want is fancy new stuff. And can quantum mechanics provide the foundation for new technologies? Absolutely. For one, there are supercomputers. Today, the basic components of computers, transistors, are reaching a size limit. A transistor behaves like a switch, sometimes blocking electrons from moving through it. However, these electrons can quantum tunnel through barriers, and switches are no exception. If transistors get any smaller, they'll stop working as electrons just quantum tunnel past them. There needs to be another way to reduce the size needed to handle info. Modern computers use bits, units of information represented by a 1, electricity is flowing, or a 0, when electricity isn't flowing. However, quantum objects can be in a superposition of 0 and 1. A 0 and 1 can be represented by different spins or polarities. Until measurement, the qubit or quantum bit is both at once, and multiple qubits can be in any combination at once. In addition, qubits can also make use of entanglement to do even more complex functions. Quantum computers, making use of qubits, have the potential to revolutionize humanity with their amazing power and speed. While quantum mechanics has proven to be extremely accurate and correct, there is one major flaw. It can't be reconciled with the other major theory of the universe, general relativity. General relativity describes gravity and the universe at a large scale. In the theory, gravity isn't a force, but an effect of mass curving space-time itself. However, general relativity breaks down at the quantum level. For one, the gravitational effect of a probability wave is not known. A major flaw is that when gravity is incorporated into the equations of quantum mechanics, infinities crop up. Scientists have tried for decades to get rid of these infinities, but have been unsuccessful. Instead, theories like loop quantum gravity and string theory were created. These theories unite general relativity and quantum mechanics, but don't describe all observed phenomena and are untestable. As a result, the quest for a full, unified theory of everything remains ongoing.